For some reason, I have to admit everyone who wants to join this meeting. I thought this happens by default.
Sir, it can be changed from the setting. This setting, host controls.
Unfortunately, so many students are trying to enter. This pop-up window comes up and I'm unable to access the controls. Okay, let me first still ask. Let me. Okay, scribes for today are ID number 1 to 6. Please note that. It would be 2050 01. Including both 1, 2, 3, 4, 5, 6. That here, I hope we have students of these ID numbers present in the meeting. Also uploaded the LaTeX template that you need to use in order to scribe. I'll announce shortly how you're supposed to submit your scribe notes. Then you can start working on the slides. So let me share my screen. Share that. I hope you can see your screen. You see my screen. And before we begin, does anybody have any doubts about the first class? Any doubts that you may have? Anybody? Okay, that's very good. Before I sort of start the class, remember in the last class towards the end, I was talking of the evaluation criteria. Right? So I have managed to discuss this with my co-instructor Rahul Butul, and we have agreed to have a project component in the course. Okay, so let me just rewrite the evaluation criteria. So tutorials and or quiz. I hope this particular white color is visible to everyone. I chose this brown color background not because it looks beautiful necessarily, but since you'll be staring at the screen for a long time throughout the day, I think doesn't sort of put too much strain on the eyes. Right. So I hope this is visible.
Yes.
Okay. So tutorial quiz stays at 10%. Scribe also stays 10%. Project component is 20%. 20% has been taken from mid-sem, which is now 20%, and the end-sem, which is now 40%. All right, so that's the final evaluation of the grading mechanism. The grading will be relative. Okay. And the way we do projects is slightly different from the way you did it in your discrete math course. Okay. So I believe I have roughly 170 students. Similarly, Rahul also has about 170 students. What we are going to do is we are going to divide you into 17 groups with roughly 10 students in each group. And rather than leaving it up to you to choose the project topic, we are going to assign each of the group a specific project topic. Okay, so you don't have an option in choosing your project topic, but we will give it to you. We hope to give you your project topics by latest, say, second week of September. Okay, and the project topics would be not too complicated, right? So that you should be able to do a good job is in whatever time is remaining. Secondly, we do not want you to waste time in making videos, right? We will consider a project report and some sort of an interaction with me or Rahul or both. That interaction would possibly be a presentation from your end or something, right? That is yet to be discussed, but at least no videos for sure, no websites. I heard that you guys made websites for your projects last semester. My aim of giving you projects is that you should focus on the subject matter rather than the paraphernalia. Right? Any doubts, any questions on this?
Sir, can we make groups with our decision, like you are
No.
giving 10?
No, we are going to divide you into groups, so the groups will also be given.
Okay, sir.
I know some of you may not get well, or some of you may want to sort of form your own groups, but think of this as some experience that you might have in your workplace eventually. There also you will not be allowed to form your own teams. Think of it that way, and it's a large team, right? 10 members, so I'm sure you'll get along with at least a few of them. Okay, so with that done, I think we need to start. Once again, we will write it down here as well. Lecture 2, describing responsibility is with these IDs. So 1, 2, 3, 6, include. Okay, so we were looking at examples of sets on which there is a binary operation defined, right? I'm not going to go through these examples once again. Right, so this was one specific set of these 4 complex numbers was another example. The idea is try to observe patterns. Okay. And I hope this was given as a homework. I hope at least some of you have tried to fill in or create this table of yourself. Once again, this is all about practice and thinking this stuff out. Okay. You think you're going to be able to solve all problems later on, just listening to videos, that's not going to do. Okay, that doesn't even apply to us. We also struggle with a lot of problems. It's equally applicable. Let's get on with this. So these are the examples where we finished the last class. As of now, we have looked only at a finite set, right? We did not consider infinite sets. So the first example over here, set of integers. I'm sure you are familiar with this notation, z with your usual integer addition. Okay, so again, what can we observe from this particular example? If we were to come up with a table, this would be an infinite table. So we do 2 times 1, 0, 1, 2, so on and so forth, and the same over here. Okay. But still observe something common with the other examples that we have seen earlier. So -2 plus -2 minus 4, -2 minus 3, minus 2. Right? So what sort of a pattern do you observe over here? This would also be something like a cyclic shift, right? Of course, there are infinite rows and columns here, but we just consider a subset or a small part, you still observe that entries are shifting to the left or the right. To the left. So -3, -2, -1, 0, so on. Okay, let's look at another example. So a more complicated one. In the first example, we could at least make an infinite table. In the second example, there is no chance. And sort of, you may find this a little strange. Why did I let go of this 0? But for now, just assume that is the set I have considered. So all real numbers except 0 with your usual real number multiplication. All right. A more complicated example. All of you know matrix inverses, matrices, right? So consider the set of all 2 by 2 invertible matrices. The matrix entries can be any real number. Okay, this set is denoted by GL2R. Okay, this R stands for what are the, from what set would the entries of that matrix come from? GL2 simply means 2 by 2, so that 2 is giving you the size of that square matrix. Okay, what GL stands for, I'll tell you a little later. Okay, but it simply means all 2 by 2 invertible matrices. Okay, so this is important here. Right, so again, there would be a similar pattern. We will now discuss what is that pattern. It's important. That is where all examples end. Can any of you give me some patterns that you can observe here? For example, let me give you the first one. In all these sets here that we have considered and all the different operations, binary operations that we have considered, if I take 2 elements, I'm just going to call them by the small letters A and B. Right? And if I perform this binary operation on these 2 elements, let me denote the binary operation by a dot here. what happens to the resultant?
We get the resultant in the set itself.
The same set itself, right? It never goes outside this set, this original set, let's call it G. Okay. In some sense, you can say I'm cheating because I've defined the operation keeping this in mind. Right? But if you look at most of these examples, I have not sort of carefully chosen the binary operations. They are what they are. For example, in this case, integer addition is not something special. We have been using this forever. Okay, so we did not sort of create this operation keeping this property in mind. Just so happens that the property holds for this particular operation. All right, and you can see that it holds true for all these three examples. The multiplication of two invertible matrices is also invertible, right? Have all of you studied that fact?
Sorry, sir, can you repeat?
So the question is, if A is a 2 by 2 invertible matrix and if B is a 2 by 2 invertible matrix, product of this two matrix, let's call it C, it will also be of the size 2 by 2, right? So what I'm
Yes, sir.
saying is, if A is invertible and if B is an invertible matrix, then so is C.
Yes, sir.
Yes, yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Great. So in that sense, this set GA2R is closed under the usual matrix multiplication. Okay. Similarly, set of reals minus 0. If you take any two non-zero real numbers, the resultant is also going to be a non-zero real number. Okay. If I look at the previous examples, for finite sets, it's much easier to see. I mean, all entries in this table are from that set. Okay, so of course, this set contains everything that we can get by using this binary operations or various combinations of your group of your elements from this set. It's true also for this example, this examples, right? So one feature amongst all these examples can say is that, let us say G is a set on which you have defined a binary operation that I'm usually going to denote by this small dot. The first feature that we can say is, if I pick any two arbitrary elements from this set G and I apply the binary operation on these two elements, then the resultant element is also in the same set G. Okay? That clear?
Yes, sir.
Yes.
Okay, so remember, what we are trying to do is we are trying to come up with a structure. Okay? We are trying to characterize the structure for which we have given several examples. So this is one property. I think I'll give you the rest of the properties directly. So this particular property that we just listed out is what is called closure. And the set is closed with respect to that particular binary operation. So that's the first common feature that we can observe in all these examples. Second is associativity. I'm sure you know what is associativity. Okay, basically means, how can I sort of convey what associativity means in common language? What does it encode? Anyone? What does this equation tell you?
If we perform the binary operation a dot b before like b dot, like
if we do the binary operation A dot B and then the resultant with binary C, that will be equivalent to B dot C and later the whole resultant with A.
Exactly. So this basically means that the order in which you perform the binary operation is not important. Right? Whether you first perform B dot C or you first compute A dot B, it doesn't really make any difference to the eventual result. Okay? That is what is associativity.
Associative.
Third property, identity. So if you again focus on these finite examples, if you look at the first row and first column, whether it is in this example or in this example, we see is that the first row and the first column is are basically the same as the elements themselves. In all examples, in fact. First column, first row, just the elements themselves. This case, and in this case, first column, first row, just the elements themselves. Column, row, exactly the elements. What does that mean? Even in the infinite examples,
The order does not matter.
so that is associativity. Now, what can one conclude from this pattern? The first row and the first column,
Sir, A dot B is equal to B dot A.
that true, let's say for this example, is A dot B the same as B dot A?
Like it denotes, like for the additive example, 0 is the identity, and
No, so
for
that's
this,
what I'm trying to say. We are trying to come up with features that are or patterns that is true for all of these examples that we discussed, not only for few of them. Right? So in this particular case, I hope you agree that A dot B is not necessarily B dot A. Right?
Yes, sir.
But so I'm emphasizing on the first row and first column. So what does the first row or first column indicate? It is the operation. So if I look at the first column, it is the result of applying this particular element or combining this particular element with any of these elements, right? That is what is the first column. Similarly, the first row is nothing but performing the binary operation of this particular element with all these elements of the group. Sorry, of the set. Still not. I shouldn't use that word. And what is the result? What do we observe?
We get the same element.
Exactly, we get the same element, right? So that is the interpretation of the first row and first column. You take a specific element and you combine with all elements of the set, with itself as well. But what we observe is you get the same element back. Okay, so it's like nothing but, we are all familiar, right? If we look at integer addition, no matter what integer you take, if you add it with 0, you get the same integer back. Similarly, real number minus 0, if I look at that set, and any element from that set when multiplied by 1, you get the same element back. Okay, so that implies identity. Okay, that in all these examples that we saw, there exists an element, I'm just denoting it as E, okay, such that for all elements in the set G, okay, all elements, which means it includes E itself also. Now, if you perform this binary operation with all elements of the set with this element E, right? So first, whether it is A and second is E, or whether first element is E and the second is A, it doesn't matter. You get back. Sorry, there is a typo there. A. Yes. Yes, there is a typo. Okay, please take a note. You get the same A back. Right? Which means that this element E has no effect on the other element, whether that other element is first or whether that other element is put second in the binary operation. Has absolutely no impact, and which is why we call that element as the identity element. Okay, and what it is generalizing is, I hope you realize, it is just generalizing the concept of 0 as far as addition is concerned, right? And as far as multiplication is concerned, it is generalizing the concept of 1. How about 2 by 2 matrices?
The identity matrix.
Right. So the identity matrix 1, 0, 0, 1. Okay. If you multiply this matrix with any other 2 by 2 matrix, whether that 2 by 2 matrix is on this side or on this side, you will get the same 2 by 2 matrix as a result of matrix multiplication. Okay. So in all these examples that we have seen, this is again a common property. And the fourth is the most non-intuitive property in some sense, which is still true, is what is called the inverse. Okay, so this property states that for each element A, okay, for each and every element A in my set G, there exists an element, let's just denote it A inverse. Okay, there exists an element A inverse in G such that if I perform a binary operation between A and A inverse or A inverse with A, you get back the identity element. Okay, and because of this property, we can call this particular element A inverse as the inverse of the element A. Right, so we can again maybe go back and look at all these examples. How about this example? What would be the inverse of, let's say, A, B, C, D? This matrix, such that this matrix is invertible. Anyone?
1 upon determinant of this matrix into adjoint of this.
What would that be?
First we have to
B
swap
minus B
the
minus C.
Yeah,
B minus B minus C.
Right. So you exchange the elements on the diagonal
Diagonal, yes.
and you negate the elements on the off diagonal. It's not very difficult to check this. Just multiply this and this, you'll get back the identity. Okay. But which is why you can now see why I chose this set. 2 by 2 invertible matrices. Yes, so in this case, you might think I'm cheating by choosing only some kind of matrices. Okay, but in general, that's not the case, right? So, for example, if I again consider the set of all integers with respect to usual addition, what would be the inverse of some integer A?
minus negative.
minus A.
Exactly. How about this case? Multiplication of reals?
Reciprocal.
Reciprocal, right? If A is the real number and it is non-zero, 1 by A is the inverse. Okay, so these are common operations and relations and features in some sets that we are accustomed with. It is those features that we observe in our mathematical objects that we play around in our daily lives that we are now trying to make it more abstract. in principle A and 1 over A and minus A, right? They are quite different things. But if we look at it from the point of view of this plus and multiplication being a binary operation, they are one and the same. If I perform the corresponding binary operation between A and minus A, it gives me the corresponding identity. If I perform the real number multiplication between A and 1 by A, I get the corresponding identity, which is 1. Okay, so again, just trying to emphasize that this is an abstract, this is basically an exercise in abstraction. Okay, so if I look at all of these examples from very close, they are sort of feel very different. Addition of integers, multiplication of real numbers, there is no real connection that way. If I sort of look at it from this abstract point of view, we are not doing anything new. Yes, and so is the case with a very different set, which is the set of 2 by 2 invertible matrices. Okay, and we can of course repeat this for the previous finite examples as well. Okay, so what is the inverse of, let's say, 1? Anyone?
1 itself.
1 itself, right? How about 3?
7.
7. So basically the idea is, in that particular row, search for the identity. Yes, this is the identity here. So 3 with what gives you the identity? 3 with 7 gives you 1. So 7 is the inverse of 3. Okay, 1 is its inverse itself. How about the inverse of 7?
3.
Inverse is 3. What is 9 inverse?
9.
9. Okay, so again you can see that this is a little strange, right? An element being its own inverse. Right? The usual sets that we have worked in our day-to-day life, which is, let's say, integers with addition, or real numbers with multiplication, complex numbers with multiplication, etc., this rarely happens, right? Again, we shouldn't sort of think it as very strange. We are only interested in finding an element, right, which is its inverse in a very specific sense. So that's the inverse. Okay. If there is this element A inverse which satisfies this, remember this definition doesn't mean that only this much is necessary. Okay. This also must happen. Only then that particular element in the inverse here is said to be an inverse. Okay.
Sir, I was having a question.
Go ahead.
Regarding the closure property, sir. Here we saw that every binary operation followed this closure property, but instead, if the binary operation did not follow the closure property, then will it be called a group?
No. So, yeah. So this is basically the definition of what is a group. Okay? So it's like the way I imagine the concept of group may have arisen is, there are all these several 7-8 examples we give, and I can find 1,000 another examples. Right? And these are not just random examples, these are examples that are actually useful in studying something or the other. And then, looking at all these examples from an abstract viewpoint, somebody may have realized that, oh, well, let me not worry about what these specific elements are. Are they numbers, integers, real numbers, complex numbers, transformations, functions, etc., etc. They could be anything, but all of them have these 4 properties in common. So if as I said, or as I demonstrated in the first class, if I'm interested in studying the relationship between elements, ignoring what those specific elements are, right, then that gives rise to this definition. So here, if you note, this set G is not chosen specifically. It could be a set of anything, any elements, functions, transformations, complex numbers, etc., etc. We are not even specifying what the elements of this set G are.
Sir, here for the case of Z pi, we consider the binary operation of addition modulo phi.
Right.
For the same set, if we considered addition as normal addition, then that will not follow that closure property, right?
Right. And therefore,
Means-
it will not be a group.
Means the group is specified by both a set and its associated binary operation.
Yes. So
Yes.
carefully read definition. Group is a non-empty set G, but that's not enough. Along with the binary operation.
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Okay. And even in the notation, if we look at this carefully, it's not just the set. You also have to specify what that binary operation is. Both put together form what is called a group. Okay, and the set and the binary operation. Right? So you can come up with a set, you can come up with a binary operation that in general may not form a group. Only if these four very important axioms are satisfied or properties are satisfied, only then we will call that set and that along with that particular binary operation as a group. Okay, and
Yes,
these
yes.
right. See, these four things: closure, associativity, identity, and inverse. They are known as group axioms. I hope some of you at least, or maybe all of you, understand the word axiom.
Yes, sir.
What does that mean?
So the fundamental properties which has been assumed.
Axiom itself, I mean, not in terms of group axioms, but axioms in general, what do they mean? What does that word mean? So what is the difference between, let's say, axiom, proposition, lemma, theorem, etc., etc.? You may have
They cannot be proved, I guess.
exactly.
Because
You may have heard the term Euclid's axiom for geometry. Yes or no?
Yes, sir.
Yes, sir.
If
Yes, sir.
you have not heard of Euclid's axiom, please Google for that. So these are sort of basic assumptions that we assume will be satisfied. There is no way in which we can prove them. Okay, that is what is meant by an axiom. Right. Anyway, so this is what these set of four axioms taken together are called group axioms. Okay. Once again, the emphasis is if you look at these axioms, the main essence is, at least one of the essences is that I am not at all talking about what the specific elements of this set G are. They could be absolutely anything. Right? Okay, so that's sort of the essence as far as I'm concerned. Then there are some specific classes of groups or types of groups, which are also very commonly found. I think some of you have already seen this. That is called an abelian group or a commutative group. Okay, what does that mean? As the word commutative suggests, it simply means that this binary operation that is defined on the set is commutative. That is the case, then the group itself is called commutative group, or a more popular name is an abelian group. Okay, so the mathematical definition is for any or for every pair of elements A and B in this group, the order in which these elements occur in the binary operation, that does not matter. Whether you perform A dot B or B dot A, the resultant is the same. Is that clear?
Yes, sir.
Yes, sir.
Some of you, I don't know, maybe wondering what does this word abelian mean? Anybody has an answer to that? Commutative group, that's a very natural term, right? I mean, if you look at the definition, it makes sense to call such a group a commutative group. What is an abelian group? Why does that mean? Where does that name come from? So this is because Indian mathematician is right. Have you heard of this mathematician before?
No, sir.
No.
Okay, so let me just give you an interesting tidbit here. So all of you have solved quadratic equations, right? Something of the form ax squared plus bx plus c equals 0. So what values can x take? Right?
Yes, sir. Yes.
We have sort of know this solution square b plus or minus square root the discriminant by 2k, right? So this is a quadratic. And the solutions are given in general. So we did not assume what is A, what is B, what is C. These are variables. In terms of these variables, the solution or the roots, as one would more appropriately call it, the roots can be given directly in terms of these variables. Okay, there is a nice closed form solution. Closed form. The unknown is directly given as a formula only in terms of what is known. Okay. How about the cubic? Can you directly give me? So, by the way, how many solutions would for x would exist here?
3 solutions.
Three solutions.
At most
Good.
3.
At most 3. Good. So, can you give me the closed form solution here?
Sir, there is
It is
a
very large.
direct solution for reduced cubic, which is of the form x cube minus px plus q.
You're saying you cannot give me a direct solution.
Yes, sir, but it is long term, means I don't
So,
remember.
okay, you may not be aware. I mean, to be honest, I also don't know the formula for this, but it exists. Okay, take that as a fact. How about what is it called? Fourth order polynomial.
There also exists for fourth order biquadratic,
Biquadratic. Okay.
but after
That's right.
power 5, there does not exist solution.
After power 5 or including
Or
power?
including power 5.
This is what is called a quintic. Ax to the power 5 whole and so forth. Okay, what is equal to 0. Okay, so surprisingly, you can find direct solutions to all of these: quadratic, cubic, biquadratic. But quintic, you cannot not just because it is hard, right? But this mathematician, Niels Abel, right, was the major contributor in proving that you just cannot solve it. So it's not just that nobody has found the solution for this as of now. Right? It is known that you cannot find a direct solution to this. And believe it or not, group theory does have a role to play here. Okay, so in his honor, the name of this group, these kinds of group was given as abelian groups. Okay, so that's just a historical remark. By the way, sadly, I think he died at the age of 30 or 32. Remember, due to tuberculosis. Really, I mean, so it's just amazing that by the age of 30 or 32, somebody did so much work of impact that his name is given to a large class of groups. Okay. Yes. Hello.
Yes, sir.
Just give me a second, guys. Okay, sorry class. So I hope I'm audible now.
Yes, sir.
Yes.
Yeah, unfortunately, there is this PG orientation going on, and I'm supposed to be coordinating there. So that is why there is a little disturbance. So let me continue. Yes, so that was a little bit of history behind abelian groups. Let's move ahead. And examples from whatever we have seen, can some of you point out the examples of abelian groups?
Multiplication and addition both.
Multiplication addition, so Z plus R star with multiplication, nothing else.
All of the
Z,
modulo.
right, all of the modules. Z5, modulo 5, right? So several examples. Okay.
Sir, what was the
So
third example?
this one U10. So U10 with multiplication modulo 10.
Okay, sir.
Got it?
Yes, sir.
How about non-abelian groups? So non-abelian groups would mean groups,
Matrix one.
right? So groups which have the binary operation not necessarily commutative. Okay, so even if for one pair of elements this does not hold true, the entire group is said to be non-abelian. Okay, right. So an example, as somebody rightly pointed out, L2 with usual matrix multiplication, right? Because I hope you are aware that matrix multiplication is not necessarily commutative. Any other examples?
Sir, that geometric one.
The geometric one, right? So symmetries of a triangle. Right? composition as your binary. Good, right? So there would be several examples of abelian groups, several examples of non-abelian groups. Without justifying, let me tell you, abelian groups are much easier to work with. I am not sure if I will get the time to justify this statement I made. Okay, so just a random statement as of now. All right, let's move ahead. Now the thing is, we have defined this structure, right? Okay, so this structure you can say we have come to after studying several examples. Okay, now that we have this abstract structure, right? I hope now it is clear whenever I use the word abstract what I am trying to say, right? I am not worried about the specific elements. I am only interested in the interrelation between these elements. Now that we have this abstract definition of a group, what? Sorry?
I'm sorry, sir. It happened by mistake.
No issues, no issues. Okay. So now what we are trying to do is, if I have an abstract group, what all can we prove about this group in completely abstract terms? Okay, so I'm not going to assume what these elements specifically are. Just going to assume I have a group and I have some binary operation. Just using this much and of course the 4 axioms. What else can I derive? Okay, so now onwards it's going to be very interesting. So please pay attention. I compare what we will do now basically like solving a puzzle. Before we do that, yes.
Sir, the identity rule of groups. Sir, so identity element should be unique or it can be more than one identity element.
Thank you for asking this question. We'll answer your question together in the next slide. Okay, just hold on. So before we go ahead, since this dot symbol is very tiresome, printing that dot, I'm doing this in LaTeX and it takes a very long time because I have to keep on writing this forever. So instead of writing A dot B, right, whenever I have a group, I want to perform this binary operation of dot between A and B, I just write AB without actually denoting this. Okay, that it becomes easier for me to type. That's all. Okay, now that let's answer this question that just arised. First proposition is, so I am assuming I have a set G and some binary operation, and I'm assuming it is a group. Okay, so once again, remember, I am not assuming what are the elements of this set G, I'm just assuming there is some set G with a binary operation that satisfies the 4 axioms. Then, right, so this is the answer to your question. I'm sorry, I still cannot recognize, I do not have the correspondence between voices and names. It's going to take a long time. But here's your answer. Group identity element as of now, remember from the group axioms, all we said is the identity element exists. But now we can prove. So this is no longer an axiom. We can prove that this identity element has to be unique. How do we show this? Anyone? I'll give you a hint. Proof by contradiction. So, can somebody start the proof for me?
First, we assume two.
Suppose we have two identity elements.
Okay, so let E1 and E2 in G be the identity elements.
Then E1 times E2 should be equal to
A
either of them. Then it is the
A
property of
A binary E1 equals to A binary E2 equals to A.
Right. So since E1 is an identity, by definition, E1 binary E2 is the same as E2 binary E1, which should be E1. Right?
E2.
No, but I'm saying E1 is an identity. So this is just using the definition of E1 being an identity, right?
So sir, E1 is identity, then E1
E2 should
into
come
E2 should be
equals
E2.
to E2.
Oh, sorry. Right. E1 is an identity. Right. Sorry. Thank you. So that means all of you are awake. Maybe I am asleep. Right. So, and similarly, I think you can now see the rest of the code. Right. Similarly, E2 is also an identity. Therefore, E1 E2 would be the same as E2 E1, which would also be equal to
E1.
1. So what can we conclude from 1 and 2?
Both are same. Even
E1 equals to E2.
2, E1 equals. Okay, so we have proved the fact that in a group there has to be only a unique identity. Done? Any doubts here?
Sir, the binary operation that we are considering in group definition, it should be defined for all n be in group, right?
Yes, yes.
Okay, so I thought of an example of 3 cross 2 matrix and 2 cross 3 matrix.
Oh
So
no, but you
then,
cannot write. No. So that
yes.
is not going to be able, right? So we should be we read the definition of the group, it should be clear. So what does closure say?
Sir, I
For
said consider the example of 2 cross 3 and 3 cross 2 matrix.
okay.
So their multiplication in one way out gives 2 cross 2 matrix, in another way gives 3 cross
Now
3
that
matrix.
what is your group? Your group is either 2 cross 3 or what? I mean,
Both, sir, 2 cross 3 and 3 cross 2
oh,
both.
but not 2 by 2 and 3 cross 3, right?
Yes, sir.
Right. So that is the issue. A dot B, if I take it to be a 2 by 3 matrix and if B is 3 by 2, A dot B will not be either a 2 cross 3 or a 3 cross 2 matrix. It would be a 2 cross 3, 2 cross 2 matrix, right?
Yes.
So it violates the closure property.
But sir, what if we consider all those? Means 2 cross 2, 2 cross 3, 3 cross 2 and 3 cross 3. All 4 types
Then,
of matrix.
yes, but can you
Then,
multiply a 2 cross 2 with 3 cross 3?
yes, sir. So that is not defined. That's why I was asking.
So that's what. So you look at the definition of closure once again. For all elements AB in my group. Okay, so this for all is very important. Doesn't say only for some A and B, A dot B should be in the group.
Okay, sir.
Right. And similarly, associativity also for all triplets ABC. Okay, so that for all is very important. Okay, let's move on with the proposition. Is this clear? So the identity has to be unique. what more can we derive from this? Not just the identity, we can also prove. Okay, remember again, this is no longer an axiom. We can prove that the inverse, and we have as of now only assumed that the inverse exists for each element, but we never said it is unique or not. Okay, but we can prove that the inverse also has to be unique. Again, guide me through the proof for this.
For one
And
element,
again,
we have two. For one element, we have two inverses.
okay, so writing the proof is also important. Please practice that. Let A be an element in G such that A1, let's say, and A2 in G are inverses of A. Next step. What does it mean when we say something is an inverse? Use the definition.
Operation on
A1
A1, so dot A1A is equal to A1 is equal to E. Similarly, 4, and A2A is the same as A2 is equal to E. Then what?
E is unique.
E is unique, so
So sir, A1 is equal to A2.
right. Then
we can multiply with the inverse, both the side.
which inverse?
Anyone.
Anyone. Okay. So remember, I have not assumed that this group is commutative. So the order matters, right? So left multiply both sides by A1, let's say. A1 into A2 is equal to A1 into A1. Next step.
We can associate A1 here.
A1
Both
into
sides.
A2.
Use associativity. Remember, this associativity is a very underutilized in some sense, but I mean underutilized in our minds, but it is heavily used, as you can see over here. So now I'm going to use associativity. A1 A2 is equal to, what is A into A1?
Identity element.
Identity.
Elements. So I just maybe write this step here because I don't have enough space. Identity. A1 times identity is E. Okay, so that is why this is equal to this. This implies E. A2 is A1, which of course implies A2 equals E. Okay,
Yes, sir.
any doubts here? Okay. See, I think the most common thing where students would make a mistake, and in some cases including me as well, is when we write this operation as dot, right, or whatever notation we use. I think we are so hardwired to addition of numbers and multiplication of real numbers. Sometimes we just assume this is like usual multiplication of numbers or addition of numbers. While, as I said, once again, we are working at a much more abstract level. Okay, so for example, we maybe just cancel these numbers out directly, okay, and that is a wrong step. A1 and A and A and A1 are numbers, and this were to be either addition of numbers or multiplication of numbers. we would have just cut AA or something like that, right? But we have to be more careful now. Okay, what more can we show? We have shown identity is unique, inverse is unique. Third fact, again, which seems to be very obvious, is the inverse of the inverse of each element is the element itself. Okay, mathematically written in this way. For every element A of my group, the inverse of A inverse is A. How do we prove this? In this sort of looks very irritating, right? The A inverse has to be A. What else can it be? But you need to prove this. And it looks very irritating or frustrating simply because, again, the culprit usually is that we are so hardwired to real number multiplication or addition, where this is obvious, that we think it is obvious in an abstract sense also. Okay, but for that to be obvious, we first need to show it in an abstract sense. Quick, anyone? I mean, it's just a one-line proof.
Sir, suppose.
Go ahead.
Sir, suppose
Hello.
B is inverse of A and C is inverse of B. Then we have to show that
Just a minute. P is inverse of A.
And C is inverse of B.
C is inverse of P. Okay.
Then we can say that A into B is equal to E is equals to B into A.
Is equals
And
to B into A. Okay.
And then B into C is equals to C into B is equals to E.
Okay. Then
A to C.
A equals to C.
A equals to C.
BA
How?
equals BC and then we multiply by BA
So
equals
you have
BC.
to BA equals BC. Then
We multiply by the inverse of B, left multiply.
so we
Pre
can C.
multiply by
Multiply
C.
left multiply by C. Then
Like
we
last
get E is
time.
equal to C.
But do you
Left
really
multiply.
need all of that? I mean, I'm not doubting your proof.
Sir,
Yes.
A into A inverse equal to E.
Exactly.
If we multiply
If we
A of
apply
both
inverse to
sides.
that, we'll get that, sir.
You don't have to apply anything, right? Okay.
We just multiply
Change
A
the
of both sides.
order.
This is done, right? I mean, that implies A is the inverse of A inverse, isn't it?
Yes, sir.
By definition of inverse. What is the definition of inverse? An element is an inverse of A if, when multiplied to A on the left or right, you get the identity. So, in this case, I am not looking for an inverse of A, I am looking for an inverse of A inverse.
Got it.
Yes, sir.
Once again, I am not saying this particular proof is wrong. It's just too much machinery. Okay, what more? The inverse of A dot D, or I'll just now onwards I'll just refer to this as AB. Okay, just understand that AB means A dot D. So the inverse of AB is nothing but D inverse A inverse. How do we prove this?
So we will take A dot B equal to C.
C. Okay. again, I think just look at the definition of inverse. I think maybe you can stare at the definition of inverse for a couple of minutes and you should be able to pull this. What do I need to show in order to show that this is the inverse of AB inverse? AB times this should be equal to
Identity element.
identity. So since I'm asking to show that, I'm not asking to find the inverse of AB, right? I'm
Yes, sir.
asking you to show that the inverse of this is this. So it's just like a verification. Isn't it?
Yes, sir.
Yeah, yes.
Post
Just
multiply by
substitute
B
it over
inverse.
here.
And after-
And
B
inverse
A inverse.
associativity.
Yes, sir.
Okay, and of course, this is something I have to show. Space this out. This is equal to this. B into B inverse is
Identity.
Identity.
okay, and are we done?
Yes.
No, no.
Hello, sir.
We have to prove the other
B
side.
inverse A inverse into AB.
Okay, we have to show that this is also identity. Of course, easy. But remember, do not skip these steps. At least maybe in this course, you should use all these axioms properly. Otherwise, it could be like you're using, or you're imagining this is just your usual real number multiplication or addition. B inverse B, this is 4. AB inverse is B inverse A inverse. Why is it not A inverse B inverse? Do you see that?
Yes, sir.
Can we
Order
change
matters.
again? We change the order. Commutative property.
Exactly. So, I mean, what one more additional property you have just proved is if G were to be an abelian group, then the inverse
Then
of
A
AB
inverse
would
B
be
inverse.
A inverse B. I think I have fifth point here, after which we won't have time. So, for two elements A, B in the group G, there always is a unique solution to the equations Ax equals B and Ya equals B. Okay, so solution in the sense I want to solve for X here and I want to solve for Y here. You cannot have more than one X and one Y from the group satisfying this. So let's take Ax equal to B. Can you show that the solution is unique?
Multiply by inverse A inverse.
Pre-multiply by inverse.
Would that be a proof? Multiply by A inverse. And again, when you write this, remember you must write left multiply. I multiply this by A inverse on the left, I get X equals A inverse B. Are we done?
Inverse is unique.
Yes, sir. Inverse is unique, so this operation
No,
will
but
also
this does not show that X is unique, right? You have to show that there cannot be any other X apart from this which solves this equation, isn't it? Please remember, the statement says that there is a unique solution. The statement doesn't say that there exists a solution. what you have done over here is you have proved that there exists a solution to Ax equals B. Why? Because for every A inverse exists in the group, and then A inverse into B has to be in G because of closure. So you have given an existential proof. The statement is about uniqueness.
Again by contradiction.
Here, that you remember this. Uniqueness is something else. So maybe let's try contradiction. So let x1, x2 be elements of the group G such that Ax1 is equal to B and it's the same as Ax2. Now,
A inverse pre-multiply.
right, pre-multiply and left multiply multiply by A inverse, which of course is unique. Remember, we are using all of this one by one, right? To get what? Get x1 is equal to x2. Okay, and I think you can prove this, the uniqueness of the solution to y equal to b yourself. Okay, instead of pre-multiplying, you have to post-multiply, that's all. Right?
Yes, sir.
Okay, and I think we stop over here. Just read out this definition. Okay, order of a group. What does that mean? It simply means the number of elements in the set G. That is what is called the order of the group. There are two notations. This I think you are familiar with. This is the notation for cardinality, right? In group theory, we will also usually use this notation, O, small o of G. Okay? So, right. So, I think that's going to be the nature of the course. Once again, I think I'm repeating this 100 times. We are not going to assume anything about the elements of this set. We are then going to prove properties and we're going to derive theorems and propositions about the abstract group itself. Right, so thank you, and I hope those who are responsible for writing, they'll do a good job of this, and I communicate how to submit the scribe notes. Once the notes are there, I'll upload the lecture slides as well as the recording of the. Thank you, and see you guys on Tuesday.
Sir?
Yes?
Sir, so there are not only two elements, means two structures of abstract algebra. There are more than that, right?
Oh, yes, yes, yes. There are, I mean, so groups,
So, sir,
rings,
fields are
fields.
also.
Yes.
So, sir, I want to tell you that in discrete maths course, we have taught about fields, finite
Okay,
fields.
so that, okay. Only finite fields or fields?
Means more focus on finite fields.
Okay.
Field of
Okay, so,
Z3, Z5, also
okay.
Z4,
So
Z9.
ZP where P is prime.
Prime and also power of prime means Z4 and
Right.
Z9 also dot.
Oh, but are they fields?
Sir, he meant about GF4, I think.
Means GF4 plus Z9.
Okay, great. So that is going to help me in the second part of this course, which is vector space. And vector space also needs a field. So great to know that you know what is a field. But yes, I mean, just to enumerate, there are like groups, there is rings, there are fields, there are modules, there are vector spaces, and some others as well that I probably don't know. all of these are different algebraic structures. Okay, Bandhan, I guess it was you, so I will
Okay, sir. Thank you.
see you.
Thank you, sir.